Thank you. Good afternoon. Peter is a tough act to follow, but I'll do my best, and I'll change topic a little bit and talk about one of the, maybe a somewhat esoteric topic in this symposium on plate tectonics, the case of large earthquakes at this, on our planet. And I'll show you how they still pose a challenge to plate tectonics and maybe give some hints on how to move forward in trying to understand them. So my talk will, first of all, I'd like to acknowledge some of my collaborators over the years, and I realize that I missed some of them, as you know, that's a dangerous list to make. But anyways, the rest of my talk will be a lot of kind of vignettes, like Xavier talked about this morning, some snapshot ideas on this topic, and hopefully you'll find some organizations through them, and we'll see where they lead. I wanted to start with this, a little bit of history with this map that we've seen, and maybe not this one, that's from the paper by Isaacs and others that was cited several times already today. And what you see here are obviously plate boundaries as they were known in 68, and arrows that indicate the slip direction of large earthquakes that had been studied at the time, showing convergence across subductions, some extension in rift zones, and motions and slip vectors parallel to large strike slip faults, in particular transform faults. And but there is one exception, right? This one is in the middle of a continent, and really my talk will be about events like this that are not at plate boundaries and that we have difficulties to explain. Nevertheless, the paradigm under which we function, regardless of whether we are at a plate boundary or within a plate interior, is that seismic phenomena, earthquakes, occur or are explained as a result of interactions and other processes at the edges of plates of lithosphere that spread apart at ocean ridges, that slide past another along large strike slip faults and converge at subduction zones. Now, when we look at, and this is, one could do much better map than this one, but if you look at the magnitude, earthquakes of magnitude greater than 6, that we have on the one of the largest available catalog of earthquakes, we see that obviously most of them are located along plate boundaries, and we know why, but a number of them are located within plate interiors. And here I want to focus on the one that I outlined in red, which strike what I called, or what actually Johnson in 1989 called stable continental regions. So I think I will say SCR during the rest of my talk to save a little bit of time. So these are areas where the continental crust is largely unaffected by currently active plate boundary processes. We're kind of leaving the realm of plate tectonics, really. So that seismicity, as you can see, is widespread. It covers pretty much every continent. There are actually some in South America that I haven't picked up here. And their temporal and spatial logic is very unclear. And still defeats our understanding, I believe, and they are a challenge to plate tectonics. They are also a challenge to hazard assessment because we don't really have guidelines within plate interiors, within SCRs, to not so much predict, of course, but determine the source areas of potential future earthquakes as we do at plate boundaries, where we know the faults, where we see that seismicity large earthquakes tend to recur at the same places. So going back to the current paradigm, or the paradigm at play for intraplate earthquakes, this is a sketch that is borrowed from this paper by Kanamori and Brodsky. This is geologic time. You can put your own scale there if you want, and this is stress on a particular fault. The red line is the strength of the fault that may vary or not as a function of time, and the black line is stress as a function of time, so stress increasing as a result of plate motions in a way that can be linear or not, until it reaches the strength of the fault, and then the earthquake occurs, the stress drops, and then there is a recovery of the stress within the vicinity of the fault, and so on. This may be more or less regular in time. But the notion here is that earthquakes occur as a result of global plate motion, and they result from the localized accumulation of tectonic stress at long-lived plate boundaries, where active faults are steady state systems with a balance that is achieved over time between the rates at which the tectonic stresses load the faults and the rates at which this loading is released by large earthquakes. That's the way we think about plate boundary faults, and for lack of a better paradigm or model, that's also the way we tend to think about intraplate or SCR faults, except that we often think of them as very, 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 very slow faults. The case I'm going to try to make is that we need to look at things in a different ways, and we'll see if I can convince you that for intraplate earthquakes or at intraplate faults, there is virtually no stress loading of those faults over time. And what I will argue is that, of course, fault strengths may vary in a way similar to plate boundary faults. A fault is a fault. But what I will argue is that while the long-term tectonic stresses, obviously, they do provide, over time, the energy that is released during those large earthquakes, the earthquakes themselves are triggered by perturbation of either stresses, or when that would be the blue line here in the schematic drawing, or when the fault strengths decrease to the point that it will hit the stress level available in the surroundings of that fault. So the notion is that SCR earthquakes, stable continental region earthquakes, occur as a result of transient stress or strength perturbation, localized, that release elastic energy from the bulk of a pre-stressed crust. And I'll show you a series of observations that hopefully illustrate that thinking. This is a fault in Oklahoma, the Mears Fault. You can see it in this Google picture here. Last surface faulting 1,200 to 3,000 years ago. Nothing that we know of in the previous 1,000 years. No current seismicity on that fault. Oklahoma, as for those of you who've been there as tourists maybe, is pretty flat, and there's no geologic or recent geological structure that is associated with this kind of feature. Another example, and this is not a fault we're looking at here, we're looking at sediments, or actually we're looking obviously at the surface here, the very, very flat topography of the upper Mississippi embayment in the central eastern U.S. This region is called the New Madrid region of the central U.S., and I'll show it to you in a bit more detail later. It's a region where large earthquakes occurred in the Holocene, all the way up to as recent as 1811, 1812, magnitudes greater than 7, not exactly known. But the point is that those earthquakes and the ones that preceded the recent ones, the historical ones, leave some sand blows, so essentially sand getting out of the ground and on top of soil and then being covered by soil. So those layers of those sand blows can be dated. Therefore, the history of earthquakes in that particular region can be known. And so, this is borrowed from an old paper by Cox and other to which we added some data. This is time here. Note that this is a logarithmic time scale in years, and these are a number of faults in SCR region, in SCRs, right? In Australia, and where they've been preserved thanks to the current very dry climate. North America, the New Madrid seismic zone, which is shown here on this line. Bhuj, India, we heard about it, and the closer to us, the Ruhr Valley Graben in in Western Europe. And each of those black boxes, is an earthquake that is recognized and dated, and there are numerous ways to do that in trenches or using sand blows. And you can see that it's really hard to find any regularity in all this. And you can even find examples like, where is it? The Meersfault, we have 2 earthquakes and then nothing since then and nothing that we know of before, or earthquakes like, again, some earthquakes in Australia where the same thing happened. So it seems to me that when I look at this data set, which of course is incomplete, those are tough to document, but that many large SCR earthquakes appear to be, first of all, many of them are one-shot events, at least at the time scale of the Quaternary, I would say. And they occur in regions, for many of them, that are devoid of any seismicity today, with landscapes that lack any geomorphological feature of active deformation today. Some of them are one-shot events, but like I said, for the New Madrid is here, a series of earthquakes in the past a few thousand years. Some may be part of a millennial scale sequence of events, and with, in some cases, interruptions that last many thousands of years. So the notion of a steady state activity in those systems doesn't seem to apply, and my claim here is that steady state earthquake activity does not persist in the long term on any single SCR faults. This is an example here of the surface rupture of the Tennant Creek earthquake, magnitude 6.7 in 1988 in north-central Australia. This is the Hebron Fault rupture, 40 kilometers long, in western Namibia. A very nice rupture, not well dated, but again, just one event that is known. Here again, one single event. So my reasoning here is that the fact that single or clustered activity that we observe, single or clustered activity on most of those systems, indicates that what we're looking at when we see those earthquakes is not the long-term behaviors of those fault zones, because over the long term, at least at the scale of the Quaternary, even more, they are inactive. So these short time interval of seismicity interrupted by gaps that can have various duration indicate that there are short-term stress or fault strength variations, and this is a hint, perhaps, that SCR earthquakes are not a direct result of tectonic stress accumulation. Otherwise, they would occur on a much more regular basis, since tectonic stresses change very slowly on a scale of millions of years. And it's also a hint, not a proof, of course, that faults in continental interiors are not loaded individually at a constant rate, in contrast to what we think happens at plate boundary faults. If this is true, this argues against interseismic strain accumulation, localization, I would say, on any individual stable continental interior fault zone. And these are things that can be tested, as we will see. So let's have a closer look at the New Madrid region of central eastern US here, where this is the outline of the upper Mississippi embayment, and this place is the locus of significant seismicity today, the red dots that you see here, and a series of earthquakes in 1811, 1812. 3 of them are roughly located by the white circles on this map. And obviously, because this area is now very populated, much more so than it was in the 1800s, it's been the focus of intense scrutiny, in particular to better quantify the level of hazard that is associated with this kind of structure in the middle of a pretty flat part of the North American continent. And you can see here the level of ground acceleration is computed in some of the, maybe not the most recent, hazard map of the central eastern U.S. with high levels of hazards. in this region because those calculations are based on the notion that these fault zones have produced large earthquakes in the recent past and will continue doing so on a more or less regular basis for the foreseeable future. Of course, yeah. So this area is instrumented very is very much instrumented with seismologists, geodesists, geologists going in the field and looking at what's going on. And in particular, it's been monitored quite a bit using GPS geodesy. The notion is that if this area of the central eastern U.S. is going to is able to produce more large earthquakes in the future, then we should see that strain building up today in order to produce those earthquakes of the future as they happened in the past. So instead of showing you a map with arrows like usually people like myself and others do in the GPS business, I want to show you a result, kind of a summary. This is publication year is in the x-axis, and this is the velocity that's been measured with geodesy over, depends for those studies, but let's say on average over a 20-year time interval. And the region is about 200 kilometers wide, so you can convert that to strain rate if you want. And you can see that there's been quite a bit of a variation, and that led to quite a bit of a debate on how much strain is building up today in the New Madrid region of the central eastern U.S. We're now converging, so some of those early estimates were conservative, not significantly different from 0, 3 millimeters per year. Some maybe took some more risk here, 6 plus or minus 1 millimeters per year, or here 2 plus or minus 1 millimeter per year. So today, where are we? We are right here, and I think everybody agrees that in the New Madrid region, we are measuring 0, so within an area that's 200 kilometer wide and over 20 years. We're measuring 0 plus or minus 0.2 millimeters per year. So no evidence for localized strain in this region, and the same holds for most places on Earth in stable continental regions where we have that density and quality of a geodetic network. So now it's interesting to compare that number, or that upper bound, let's take the upper bound of 0.2 millimeters per year with what we know of the paleoseismicity of the regions. We've had the 1811, 1812 earthquakes, and there is a history of Holocene earthquakes in that region, at least for the past 5,000 years. So you can plot here the strain accumulation rate that is required to produce earthquakes of magnitude 8 for those, or 7 for the lower ones here, for a given recurrence interval. So essentially, this is how much you put in the bank, and this is how often you withdraw from the bank and how much you withdraw every time. And the 0.2 millimeters per year upper limit is here. So GPS is telling us that we can't go over this, at least over the past 20 years. And the paleoseismological constraints are this gray area here. And you can see that what the paleoseismology is telling us is that the recurrence time of those events, magnitude 7 and greater, is 500, maybe 1,000 years. Whereas, well, let's take a low magnitude 7 earthquake, 1 meter of slip. This is a coseismic slip in meter. The upper bound of geodesy can tell us that we should be able to afford only 1 earthquake in, 7 or 8,000 years. So there is a discrepancy here between the money that goes in the bank and the how often and how we've been able to draw money from it. So this is an indication, again, not a proof, that we're looking at a system that is not that steady state. That's one thing. And also that the recent earthquakes, the Holocene earthquake that occurred in this region, given the very low strain accumulation rate, must have released strain that is somehow fossil strain stored in the elastic crust of this region. So no strain rates, significant strain rates that we can measure in the New Madrid. What about the whole continent? We've seen maps of GPS sites in North America. This is the raw data. This is what it looks like when you look at GPS velocities and you remove, in a very simple way, a rigid plate motions. This is 2 millimeters per year for scale. So these are deviations deviations with respect to rigid plate motion. If you filter that a little bit, then you can see a pattern here that looks very much like, well, nothing going on in the mid-continent itself, and this convergence at up to 1 millimeter per year that is the result of glacial isostatic adjustment, actually. You convert this to strain rates, and this is what's done here. Blue is compressive, and red is blue is extensional. These are the principal axes of the strain rate tensor, and red is extensional. You find the extension that is related to the correlated with the uplifting area of northern North America, and you can see the forebulge here of the rebound that is compressing, and this is also very consistent with glacial isostatic adjustment models if you find the right, if you tune the right parameters for the Earth structure. But the point here is that the area that's deforming at the fastest rate today is not the area where the largest number of earthquakes are occurring today. It's actually the opposite. So high strain rates, low seismicity, well, relatively high seismicity and very low strain rates. So there is intraplate deformation. GIA is one manifestation of that. It does not correlate with current seismicity here in North America. The same holds for Scandinavia today. So again, just a hint here, maybe we should think about strain accumulation and strain release as two different processes, decoupled processes, contrary to plate boundaries where they seem to work hand in hand. Let's keep going. This here is a map of stress direction from this paper by Hurd and Zobak, derived from some of them, not all of them, from earthquake focal mechanisms. You can recognize the beach balls that Peter was showing earlier. So this is a plate-wide view, if you want, of the stress field in eastern North America. And what strikes me here is that the stress field is very consistent over very long distances. And the four snapshots here are focuses on Oklahoma, where and the scale is hard to see here, but this, for example, this is just 10 kilometers here. And here we're looking at small earthquakes that have been triggered by human activity, essentially reinjection of fluids after fracking operation. And these reinjections do trigger seismicity, and you can see how well behaved those focal mechanisms are as well. So this gives really the impression that the tectonic stress field over a very broad area, whichever scale you look at, is very well behaved. And when I talk about tectonic stress here, or ambient stress, or background stress, or static stress, what I talk about is the combination of forces that result from natural variation of gravitational potential energy that includes ridge push that we heard about this morning, traction at the base of the plates, and tractions along the plate boundaries in the far field. So these tectonic stresses, obviously, they vary very slowly with distance, and they vary also very slowly with time, at least at the time scale of the Quaternary or the Holocene, which is what is of interest in this particular presentation. But obviously the crust has to break with mechanisms that are imposed by the static ambient field. So these earthquakes that we see today in stable continental regions, there is no doubt that they release this static ambient stress. The question I ask is whether this means necessarily that the static ambient tectonic stress is responsible for bringing individual faults in these contexts to failure. Okay, so this is a map of Oklahoma. Here you may recognize the shape of that state with what's that called, the panhandle, I think. Texas is just behind, to the south, I'm sorry, and this is the Mears Fault here. This is seismicity 1973, 1990, 1991, 2005, in 2006, 2015. We've seen this seismicity pick up, and it's been the subject of a lot of debate at the beginning, and I think now a lot of fundamental work on what does it take to reactivate a fault, even in a region where there is obviously no tectonic activity. There were claims early on around 2010, I believe, that those earthquakes were natural. That it was like maybe a tectonic swarm or crisis, but obviously they are related to wells, and now they're well understood in terms of fluid injections and diffusion through the crust and into faults that then are activated or reactivated. So there is no doubt that it is possible, even with those injections, even at those very small stress levels, to trigger faults that are well oriented in the overall stress field, for example, by injecting fluids into them. This is another example in the New Madrid, so we're going to the north of this area where, please go and read this paper because it's a bit complicated to explain in a short amount of time, but what we've done here, we've looked at the seismic catalog over the past, over 16 years here, during which the earthquake, the seismic network had not changed very much, and the completeness magnitude was pretty much constant. And this is seismicity bin by, I think, I forgot now, is it 10 days? Maybe no, these are, maybe 10 days bins. This is the position time series, the vertical position of a GPS site, and that is within the New Madrid region. And this is the water level of the Mississippi River. And you can also use plot, if you want, a fourth panel that would show the water, the equivalent water height measured by a satellite, a gravity satellite like GRACE, for example. It would mimic exactly this here. These are annual stacks, month by month. So every year we take 1 month of earthquakes or displacement or river stage, and we compute the sum. And the first thing you can see here, let's look at the easy part first, is that obviously there is a seasonal signal in the vertical displacement, in the amount of water in the Mississippi River, and they are anti-correlated. That's because the water is loading the crust, and the crust is responding by subsiding during those periods of high water level, and the opposite occurs, a rebound, during the drier periods. And that's pretty clear here. And you can see also in this stack that there is a signal that emerges from the seismicity as well. It is not obvious when you look at this plot, but it is there. And if you read the paper, you'll see the statistical tests that show that it is there. A little more fancier of an analysis here, where we try to extract the spatial-temporal principal components of those time series. And again, we see that the two main modes of variabilities of those time series is an annual mode, which is shown in red here, for the seismicity, for the displacement, and for the water height, and in blue, a pluriannual, multi-annual mode that you actually see with your eyes, I think, in the seismicity here, and that you may also see with your eyes in the GPS displacements. So the point we make in this paper is that the faults in these regions, or at least the one that rupture during those are small earthquakes, really small earthquake for some of them. I think the completeness magnitude is on the order of 2.5 or something like this. Those faults or those events are modulated by the load of the water. You see that there is a perfect synchronicity, or in phase or out of phase, between the loading and the response of the crust to those earthquakes. So the message here is that we're dealing with a system that's very close to failure, and really tiny stress changes. These would amount, in terms of stress changes at seismogenic depths, to a few kilopascals only, are able to trigger those very, very small events. Yeah, so we're dealing with a system, and of course we're not the first ones to say that. It's been known for a while and publicized a lot by Mark Zobak, for example, and his group, that earthquakes can be easily triggered by small stress changes. Those small stress changes, they are superimposed onto the background tectonic, static, ambient, whatever, static stress field that varies very, very slowly with time and space. The second point here is that this is telling us that faults in stable continental interiors, at least the ones that are well oriented in the current stress field, are at failure equilibrium in this pre-stress crust that is, however, able to sustain large differential stresses. So one more example of and that's a more recent event of earthquake in a stable continental context. This is an earthquake that occurred in Botswana in about a year ago, a little more than a year ago, magnitude 6.5. It's the largest recorded SCR earthquakes over the past 40 years, since the Tennant Creek earthquake in Australia in 1988. It's a normal faulting event within a province that is in a tensional state of stress, tectonic stress. It doesn't have anything to do with the East African Rift, which is more than 1,000 kilometers away and stops about somewhere here. It occurred within the Capval Craton, whose structure, petrological and thermal structure, is well known because it hosts, among other things, diamond mines, and so it's been studied quite a bit. This earthquake, so we studied this earthquake with colleagues, and the work of Romanowicz, for example, shows this interferogram. So we used SAR images, or Romain used SAR images to determine the depth of the earthquake and also the mechanism of the earthquake, though the agreement was pretty good with the original CMT mechanism. The signal due to the earthquake is this little bean-like blob here. The red dots are the aftershock, the early aftershock sequence. And the work that we did then, or that Romain did then, was to try to invert this for this information of surface deformation, co-seismic surface deformation, for the mechanism of the earthquake, and most importantly, the depth of that earthquake. And we were a bit surprised because the early depths proposed by the USGS were in the lower crust, which seemed a little odd to us. One last point here, you can see those tiny red arrows here. These are GPS measurements in the region, not as many, of course, as there are in the US, but they show rigidity of this region, so lack of strain accumulation at the 0.4 millimeter per year level over this area, for what that's worth. So then, if we plot this as depth here, and this is the probability density function of a series of models that fit this data, you see that the peak here is around 25, 28 kilometers depth. So this is, and we know that in this region, the MOHO is at 35 kilometers. So the earthquake occurred within the lower crust, and the questions we were asking is, how come an earthquake occurs in the lower crust where things are supposed to, or the rocks are supposed to flow, or are they supposed to flow? Or is this telling us that the temperature is such that they are not flowing, or that the petrology of those rocks are such that they are particularly strong? It turns out that we know from our colleague seismologists that the rheology of the lower crust in this region is felsic. So it's hard to make a case for stronger rocks with feldspar-rich, mafic rocks that would be located at those lower crustal depths that would be then strong enough to support large differential stresses. This is the heat flow is known pretty well at the surface, and these are some geotherms that we calculated here. And here, as a function of depth, differential stress, two friction laws for a pore fluid ratio. Yes, a pore fluid ratio of 0.37, that would be the hydrostatic pore fluid ratio, or a pore fluid ratio of 0.85, so sublithostatic. And two flow laws here, one that's kind of one of the standards we use for dry quartz, and another one derived from synthetic quartzite here. And the farthest down, we can bring the flow law in this context with this constraint, which we hope is correct, that the lower crust is made of felsic material in this region actually this line here, the dotted line here, that would be for a very low 40 milliwatt per meter square heat flow measured at the surface. So the point here is that at the depth of 25 to 30 kilometers, it's really hard to imagine how to break those rocks that are supposed to flow, unless, of course, one goes from this blue line to the 0.37 blue line to the 0.85, which requires somehow then overpressure, fluid overpressures. So I know it's like a trump card because we don't see those fluids, we don't know if they're there. It's just that we need them, or at least it's possible to explain that earthquake invoking fluid overpressure. If this is right, it means that those fluids are coming from deep. They are obviously not meteoric fluids. And I think there's a lot to explore in terms of the role of deep fluids coming from the mantle in the triggering of earthquakes in stable continental regions and elsewhere. We know they play a role, for example, in the East African Rift. So more hopefully about fluids, deep fluids, and earthquakes in the future. One last vignette. So far I've talked about the triggering of earthquakes, and I've made the assumption that, well, I've said earlier that there may be fossil strain in the crust that is available. This is the Parvi fault, a reverse fault in Scandinavia. Reverse faulting in Scandinavia 10,000 years ago. There are several earthquakes that were well mapped that had that type of mechanism. They all occurred in this region of northern Scandinavia, in a region where at the time, if we had made GPS measurements, we had measured extension. This is a result of a GIA model that shows extension in a region where a series of reverse faulting earthquake occurred, and those earthquakes occurred because the stress changed, normal stress decreased, as a result of the melting of the ice sheet. So we can explain those earthquakes, we can explain why they occur, but why were they reverse faulting earthquake in a compressional environment? What I'm showing you here is a long-term tectonic stress with a compression pretty much perpendicular to the direction of Scandinavia here, and what we think this is indicating is that these end glacial faults 10,000 years ago, they did not release the strain that was building up at the time. It was extensional, but strain that had been stored somehow in the elastic crust over time scales longer than observable by geodesy or paleoseismology. So in summary, there are some testable hypotheses in this crazy story I just told you about, and I may be completely wrong, but I think we need new guidelines to understand those earthquakes in plate interiors. And one of the testable hypotheses is that these earthquakes do not persist on any single faults, that those faults do not localize stress or strain today, that they are at failure equilibrium, at least for those that are well-oriented, and that there is a reservoir of fossil strain that is stored in the crust. And then the last point is the triggering mechanism. So I leave you with this implication slide here as a conclusion, and you may recognize the duck rabbit picture here of Kuhn. It's quite possible that we need a change of paradigm for or a new understanding of these, or an understanding of those SCR earthquakes. Thank you.